Good morning, good afternoon, good evening, depending on where you are getting us from. Welcome again to another yet exciting lecture on solar power engineering. This wraps up all the 4 lectures that we've had on lecture 4. Today we discuss and talk about peak sun hours, PSH, in relation to solar PV energy production estimation. So we look at how we transition. Just a recap, earlier on, we understand that irradiation comes from the sun. The source of energy is the sun. Then we know about the albedo for surfaces, for example, clouds, sand, or snow. Then we also have direct, diffuse, and global irradiation. Then we also know the solar constant. We've been discussing and talking that energy is transferred from the top of the Earth atmosphere to the surface. So we can have production daily, weekly, monthly, and yearly. Of course, energy is simply power times time. When it comes to the production cycle or the curve, we simply apply calculus to determine the area under the graph. So earlier on, we've used a calculation approximate where we've extracted a triangle. So we transition to another one where we equate our production cycle into a rectangle. So we have got a peak value that we consider with an equivalent sun hours, So this extrapolation gives us a principle of the peak sun hours or the equivalent sun hours that can give the energy equivalent to our cycle of production. So when we move forward, this is what we are actually illustrating, that the energy for our curve, for our graph, is equal to the energy that is under our rectangle. So we would want to simply just use the area of a rectangle, which is length times breadth, or L times B. So this equivalent sun hours and the peak actually will give us the total energy that is equivalent to the area under the graph. So what is this equivalent sun hours, or what is this peak area? So what we are actually saying is it's the number of hours for one sun illumination per day. What we are saying is that at STC, we have 1000 watt hour per square meter per day. So in terms of applying the area under the graph, if we use our original production cycle, what we are saying is that it's the integral of the irradiation, total irradiation over a day, divided by the irradiation of 1.5 air mass. 1.5 air mass. So if a location says receives 8 kilowatt hour per meter square per day of this irradiation, of this equivalent irradiation, what we are saying is this location is able to receive a 1 kilowatt per meter square of illumination per day for 8 hours. So this is the interpretation. But again, it's this type of illustration that gives us the peak sun hours that we have. If we move further, let's see how we arrive at that. If we are to follow the exact illumination that is happening for a particular number of hours. If sunlight is received at an irradiance of 1000 watts per square meter for 2 hours, 600 watts per square meter for 1.5 hours, and 200 watts per square meter for 1 hour. Calculate the total radiation per day and also the peak sun hours. So the approach is basically to consider for each cycle 1000 for 2 hours, 600 for 1.5, and 200 for 1 hour. So we find that the total radiation is 3100 watt per square meter per day. But then we realize that at STC conditions, we have 1000 watt per meter square per day. So this gives us a total radiation of 3.1 or 3100 watt per square meter per day. So the peak sun hours is actually 3.1 PSH. Then if we move on, we can actually extract the peak sun hours or equivalent sun hours for different locations. If we look at Zambia, Zambia gives an average radiation level of 5.5 kilowatt hour per meter square per day. We are saying 5.5 is the peak sun hours. If we look at India, which is quite big in size, and also you expect to have variation. So the summer radiation level is about 3 to 6.5 kilowatt hour per meter square per day. This is published in the paper by Jamil in 2016. Of course, others have quoted to say on average. So on average, we actually consider the entire 365 days. You can actually have highs and lows. So if we take the average rate, it varies between 4 to 7 for India, 4 to 7 for India. Then if we look at Sweden, it varies between 2.4 to 3.2. If we look at Australia, it varies between 3.7 and 6.1. So the peak sun hours actually can be utilized to estimate the production. For example, if it's in Zambia and we install a system, say 1K. So from a system of 1K or 1000 watts, we can actually have 5.5 kilowatt hour per day. This is how one would use the average radiation. Of course, if you have got the average radiation per month or per day, you can actually use that to do the estimation. So we've actually looked at the two approximations. So you can actually use this data, or you can actually use this data. Also, understanding that the other approximation where we use the triangle, you can actually use the actual sun hours, the average actual sun hours in a year. Then where you have the data and you can easily obtain the equivalent of peak sun hours, then you can use the peak sun hours actually for the design. So this basically wraps up our lecture 4, which looked at the estimations on PV production. So next on, we move on to the other part where we start to look at some of the practical scenarios and also look at the balance of power. So we start to look at all the other components that are there. So it's been quite some time that we've looked at production estimation. So from myself for now, until the next lecture, lecture 5, it's bye for now. And thank you for your attention.